will start this next section with a brief introduction to UCA and IEC 61850, and then focus on the Universal Relay's implementation of the IEC 61850, GSSE, and GOOSE peer-to-peer communication services. To learn more about the UCA or IEC 61850 protocols, students are encouraged to visit these websites. To better understand these protocols and where each service is used, we'll start by developing a model of the utility communication architecture. A typical substation consists of several parts, the first being switchgear and the associated CTs and PTs. Another part is the protective relays, which are now more commonly referred to as intelligent electronic devices due to the embedded enhanced functionality such as programmable logic control, communications, waveform capture, and event logging. The last two parts are the local graphical human-machine interfaces and the substation controller and/or data concentrators. These last three parts are all optional. The communication links between these devices vary greatly, but fall into the following three major categories: communication between the devices within the substation, communication between substation devices and the control center, and communication between clients at the control center. For many years, the goal for utilities in both North America and Europe has been to define a substation communications infrastructure that will allow seamless, vendor-independent integration of the IEDs and higher-level devices, such as the substation HMIs and the control center clients. Within IEC 61850, the communication infrastructure has been grouped into three areas: the substation to the control center, the station bus, and the process bus. IEC 61850 also supports what is termed as self-description. This term refers to the ability of a device to display its data to a client browsing the device's contents. Integrators and those that configure a large number of IEDs from different manufacturers were looking for a common set of configuration tools. In response to this need, IEC 61850 has defined a substation configuration language that will accept XML files from each vendor's product containing the product's configuration information known as the ICD. The configuration software can extract the ICD portions of the XML file from each device and allow the user to create an overall system configuration. This system configuration is called a CID file, which will be loaded back into the XML file for transfer back into each relay. Let's take a look at the substation bus peer-to-peer messaging services. A digital exchange between relaying equipment has traditionally been accomplished through hardwiring of the digital inputs and outputs of the relaying equipment. This method of digital information signal exchange is expensive in terms of the number of additional inputs and outputs required by the relays and installation costs. A high-speed, multi-vendor peer-to-peer communication standard was developed, known as Generic Object-Oriented Substation Event Messaging, or GOOSE messaging for short. At a later date, IEC 61850 enhanced this standard and kept the name GOOSE. The previous unenhanced version of GOOSE was renamed Generic Substation Status Event, or GSSE for short. The universal relay can be configured to support either one, but not both at the same time. At present, the relay can transmit the status of up to 64 remote outputs within one message. The media used by the communication service is Ethernet. All universal relays have both a remote output and remote input memory area for the data exchange. The communication service works in the following way for both GOOSE and GSSE. The universal relay transmits the status of all of its own remote outputs in what is called a multicast message under three conditions: when the relay first powers up, any time one of the outputs changes state, and after a programmable elapsed time since the last transmission. Upon receiving a multicast message, any protective relay can extract and store the transmitting relay's relevant remote output status information in its local remote input memory area. The universal relays can store the status of up to 32 remote outputs from up to 16 different relays within its local remote inputs table. This method of data exchange is referred to as publisher-subscribers. The typical time taken for the encoding, transmission, reception, and decoding of a GSSE or GOOSE message from one universal relay to another is typically in the quarter cycle time frame, or approximately 4 milliseconds. The objective of this lab is to familiarize the student with the procedure for configuring universal relays to transmit and receive IEC 61850 GSSE messages. We assume the student has a good understanding of the universal relay and its menu structure, as is covered in both the UR Apps 1 Interactive Learning CD and the Universal Relay Platform course. In this lab, the status of Control Push Button 1, located on Universal Relay 1, will be transmitted via a remote output within a GSSE message to Universal Relay 2. UR2, upon receiving the message, will extract the appropriate remote output, store it in a remote input, and display the status of the remote output on one of UR2's user-programmable LEDs. In order to complete this lab, the student requires 2 universal relays equipped with Ethernet ports, a multi-link switch, a computer preloaded with the UR EnerVista setup software, and the appropriate Ethernet cables. First, we need to set up and test the Ethernet LAN using the ping command as described in earlier lab exercises in the Ethernet section of this CD. Once this is done, we will configure UR1 to transmit GSSE messages. To start, let's launch the EnerVista UR setup software. From the Settings menu, select the Product Setup menu, and then open the Communications menu. Within the Communications menu, select the IEC 61850 configuration menu, and then the GSSE GOOSE Settings menu. Now set the Remote I/O transfer to GSSE. The default GSSE update time sets the maximum desired elapsed time between GSSE remote output multicast messages. The range of the setting is between 1 to 60 seconds. For the lab exercise, this should be set to 1 second. This setting will also be sent as part of each GSSE remote output multicast message, as it is used by receiving relays to determine if the transmitting relay is still communicating. We'll discuss this in more detail later in the lab. Each multicast message must contain a 1 to 20 character name of the sending device. To program this name, open the Setup menu and then the Installation submenu. Note that the name is case sensitive. We will use the name 1 entered in lowercase. The next step is configuring UR1 such that the status of a remote output will be driven by Control Push Button 1. From the Product Setup menu, select Control Push Buttons and enable Control Push Button 1. Save, and then exit the menu. From UR1's Settings menu, select the Inputs/Outputs menu, and you'll notice that there are 2 types of remote outputs. The first is called Remote Outputs DNA Bit Pairs, and the second is called Remote Outputs User Bit Pairs. During the early days of UCA 2.0, a distinction was made between the roles of the DNA and user remote outputs. Today, their function is the same. Bit pairs refer to the fact that the status of each remote output is stored in the form of a 2-bit pattern. To store the status of Control Push Button 1 in User Remote Output 1, first select the Remote Outputs User ST bits. Within the window beside User ST1, select the Control Push Button 1 ON operand from the list of operands, and save this setting. Now, each time Control Push Button 1 is pushed or released, the status of User Remote Output 1 will change state, which will result in Relay 1 transmitting an IEC 61850 multicast message containing UR1's remote output. We will now configure UR2 to receive and display the status of UR1's remote output. Start by establishing communications through the EnerVista UR setup software to UR2. Now, from the Settings menu, select the Product Setup menu, and then open the Communications menu. Within the Communications menu, select the IEC 61850 configuration menu, and then the GSSE GOOSE Settings menu. The Remote I/O transfer should be set to GSSE. At this time, UR2 will only be required to receive remote output messages, and so setting the default GSSE update time isn't necessary, but we'll set it to 1 second anyway. Next, we need to enter a unique relay name for UR2, and so from the Settings menu, select Product Setup and then Installation. We will use the name 2, entered in lowercase. Save all settings and exit to the main Settings menu. From the Settings menu, select the Inputs/Outputs menu and then the Remote Device menu. Within this menu, there is room to enter up to 16 names. Here, the user can enter the names of all relays that UR2 should accept remote output multicast messages from. In the entry window beside Remote Device 1 ID, enter a lowercase 1, which is the name that was programmed into UR1, and save and close the window. Now open the Remote Inputs menu. The remote inputs are used to store the status of selected remote outputs contained within received multicast messages. Each of the 32 GSSE remote input storage locations has an entry for a name, the bit pair default state, and events. We will enter 1 as the name of the relay the remote input is coming from. This corresponds to the name we set for UR1. The status of the control push button is located within user bit pair 1 of the multicast message transmitted by UR1, and so user ST1 will be selected for the bit pair. The Remote in 1 default state setting defines the logic state if the local relay has just completed startup, or the remote device sending the point is declared to be non-communicating. The following choices are available for the default state: on, off, latest on, and latest off. Let's take a moment to understand these default settings. The remote device, in this case UR1, is declared to be non-communicating if the local relay hasn't received a multicast message from the remote relay for a period of time equal to 3 times the default GSSE update time. This time is included in the last multicast message received from the remote relay. In our lab, UR1 was programmed with a default GSSE update time of 1 second. Therefore, if UR2 hasn't received a multicast message from UR1 for 3 seconds, UR2 will declare UR1 as non-communicating and will set the associated remote inputs to the programmed default state. Setting Remote in 1 default state to on defaults the input to logic 1 if UR1 is declared to be non-communicating. A setting of off defaults the input to logic 0 if UR1 is declared non-communicating. A setting of latest on freezes the input at the last logic state if UR1 is declared non-communicating. If the latest state is not known, as would be the case after UR2 powers up but before the first communication exchange, the input will default to logic 1. A setting of latest off freezes the input at the last logic state if UR1 is declared non-communicating. If the latest state is not known, as would be the case after UR2 powers up but before the first communication exchange, the input will default to logic 0. For both the latest on and latest off settings, when communication resumes, the input becomes fully operational. We will set the default to on. Normally, the change in state of a remote input should be recorded in the event log, and so we will set events to enabled for remote input 1. Select Save and exit the menu. As a final step, UR2 will be configured to display the status of remote input 1 on user programmable LED number 2. To accomplish this, from the Settings menu, select Product Setup, User Programmable LEDs, and again select the User Programmable LEDs submenu. For LED number 2, select the operand Remote Input 1 On, and save all settings. To test the operation of our GSSE Remote I/O configuration, simply press User Push Button number 1 on UR1 and observe that the second user LED on UR2 illuminates. If UR2's Ethernet connection is removed, user LED number 2 will illuminate after 3 seconds corresponding to Remote Input 1's default configuration. If the connection is re-established, user LED number 2 will again display the status of Control Push Button 1 on UR1. This communications mechanism can be very fast. When using universal relays, the total time from the remote output's change in state triggering the transmission of the multicast message to the reception and storing at the receiving relay is typically around 4 milliseconds. To prove the speed, the student could configure UR2 to retransmit the status change back to UR1 and use its oscillography to measure the round-trip time. The objective of this lab is to become familiar with the correct procedure for configuring the IEC 61850 GOOSE peer-to-peer messaging service. This lab assumes the student has a good understanding of the universal relay and its menu structure, as is covered in both the UR Apps 1 Interactive Learning CD and the Universal Relay Platform course. The IEC 61850 GOOSE peer-to-peer communication service is an enhanced version of IEC GSSE peer-to-peer service with the additional ability of assigning priority and what is called a tag to the multicast messages. The priority can range from 0 to 7. A priority value of 1 is the lowest level of priority that can be assigned to a message. A priority value of 0 indicates that the multicast message has the default priority, which is also referred to as best effort. Best effort has a higher priority than 1 and a lower priority than 2. The level of the message priority increases as the priority value is increased from 2 to 7, with 7 being the highest priority. The tag will allow the use of what are called tagged virtual LANs, or VLANs. Until now, you may have considered that the logical connectivity of the LAN was equal to the physical connections. By logical connectivity, we mean two devices that can exchange data. Virtual LAN technology allows us to separate the logical connectivity from the physical connectivity. The devices are still connected via physical cables, but the connectivity is now controlled through the VLAN configuration software of the devices. The VLAN can be port-based, meaning the VLAN is determined by the physical switch port the device is connected to. The VLAN can also be tag-based, meaning that a tag is sent as part of the message, with the tag determining which VLAN the message will be sent to by the switch. We'll start by configuring the switch's IP address, tagged VLANs, and priority. The easiest way to configure the switch is to use a cable. It consists of 3 conductors terminated at either end in a 9-pin female D-type connector. Pins 5 of this cable are connected together, while pins 2 at one end are connected to pins 3 at the other end. Once you have the correct cable, the computer serial port can be connected to the serial port of the multilink switch. We will be using the Hyper-Terminal application to configure the switch. This program is found in Windows under Programs, Accessories, Communications, Hyper-Terminal. Once the Hyper-Terminal application is launched, you'll need to cancel Hyper-Terminal's dial sequence by clicking on the Cancel icon. This will allow you to access Hyper-Terminal's configuration menus. Select an icon and name for the new Hyper-Terminal configuration. Then, select the computer serial port that is connected to the multilink switch and click OK. Now set the baud rate to 38,400, the data bits to 8, parity to none, the stop bits to 1, and flow control to hardware. Then click OK to attempt communication to the multilink switch. At the multilink prompt to log in, press Enter. The default login name is Manager, and the default password is Manager. Once logged in, the prompt will change to the model number of the multilink switch you're connected to, indicating a successful login. The instruction manual for the multilink provides a list of all instructions. A valid IP address and subnet mask can be programmed into the switch using the ipconfig command as follows. We'll enter ipconfig space IP equals, followed by the IP address. Then type space mask equals, followed by the subnet mask, and then hit the Enter key. Once the switch has completed a reboot, the new IP and subnet mask will be in effect. We'll command the switch to reboot by typing reboot, followed by the Enter key. The switch will prompt you for a confirmation to reboot, at which time you will type Y and use the Enter key to confirm the reboot. The switch will then prompt you to indicate whether or not the switch should save the new settings, which will include the new IP and subnet mask. You will again enter Y to confirm saving the new configuration. Once the switch has rebooted, you will need to log in again. To confirm that the IP address and subnet mask were saved correctly, type Show Setup, followed by the Enter key. The multilink switch will then provide an on-screen list of the switch's settings, including the switch's IP address and subnet mask. Once you've verified that both are correct, we'll move on to the configuration of the VLAN and priority. The easiest way to configure the VLAN and priority is through the switch's website. First, we must ensure that the computer has a static IP address. After connecting the multilink switch onto the Ethernet LAN, ping the switch's IP address to ensure that the switch is communicating correctly on the Ethernet LAN. Next, launch your preferred web browser and enter the switch's IP address to go to the switch's web page. At the Multilink's login web page, enter the default login name, which is Manager, then enter the default login password, which is again Manager, and click on the Login button. If you have successfully logged in, you'll be presented with a graphic of the particular multi-link switch you're connected to. In order to assign a VLAN tag to a particular physical port, we need to know the number assigned to the physical port. To determine the assigned port number, proceed as follows. First, determine which physical ports are to be part of the tagged VLAN, and then note the port names which are displayed on the home screen. In our example, we want ports B3 and B5 to be part of the VLAN. Once this has been determined, open the port submenu. Using the arrow keys at the bottom of the screen, move to the screens with matching port names and record the port numbers. In our example, the port named B3 has been assigned port number 11, and the port named B5 has been assigned port number 13. Now open the VLANs menu and select the Type menu. In this menu, set the VLAN type to Tag, and then click Save. We can now proceed to the Tagged-based VLAN menu. From this menu, we can see that all ports have been assigned to a default tag of 1. To create a new tagged VLAN, select Add. From this menu, enter the new VLAN ID or tag and the name of the VLAN. We will use a tag of 2 and a VLAN name of GOOSE2. Left mouse click on ports 11 and 13 to add them to this new VLAN. Once complete, select Save, and then OK to exit. You'll notice that the status of the VLAN named GOOSE2 is displayed as Pending. Select the Status menu. To start operation of VLAN GOOSE2, we'll set the VLAN ID to 2, the VLAN status to Start, and select OK. You'll notice that the new VLAN is now active, but ports 11 and 13 have been removed from the default VLAN. You can add them back into the default tagged VLAN 1 so that they're part of both VLAN 1 and VLAN GOOSE2. To do this, select the Configure icon for the default VLAN. Then add ports 11 and 13 to VLAN 1 by checking the corresponding boxes. Then select the Save icon at the top of the screen Then select OK to return to the main tagged VLAN menu. Note that ports 11 and 13 are now part of both VLAN 1 and VLAN GOOSE2. Now that the switch has been configured, we'll turn our attention to the universal relays. We will first configure UR1 so that when Control Push Button number 1 is pressed, the status of User Remote Output 1 will change to a Logic 1 state, resulting in UR1 transmitting a multicast IEC 61850 GOOSE message. Let's verify the connection of the relays to the multi-link ports configured for tagged VLAN GOOSE2. Now launch the EnerVista UR setup software and connect to UR1. From the Product Setup menu, select the IEC 61850 menu and then the GSSE GOOSE submenu. Set the Remote I/O transfer to GOOSE, the default update time to 1 second, and the GOOSE VLAN priority to the default of 4. The GOOSE VLAN ID must match the setting of the multi-link switch, and so it will be set to 2. The GOOSE Transmit E-Type App ID setting allows the selection of a specific application ID for each GOOSE sending device. This value can be left at the default of 0. The name of the relay transmitting the GOOSE message is configured within the installation menu. Open the installation menu and enter 1 for the relay name. Save all settings. In order to have UR1 transmit a GOOSE message containing the state of Control Push Button 1, we'll again assign a remote output status to be driven by this push button. From the Settings menu, select Input Outputs and then Remote Outputs User ST bit pairs. Within this menu, set the operand for User ST1 to Control Push Button 1 on. The next step isn't necessary for UR1 to transmit a GOOSE message, but if UR1 is to receive GOOSE messages from UR2, then UR2 must be defined as a remote device within UR1. In order to do this, open the Input-Output menu and select the Remote Devices submenu. In the window beside Remote Device 1 ID, enter UR2's name, which will be lowercase 2. We'll set the remote device VLAN ID to 2, which will match UR1 and the multilink switch. The remote device E-type application ID will be left at the default of 0. Once all settings have been saved, we are finished with UR1's configuration. The next step is to configure UR2 to accept GOOSE messages from UR1. First, make sure you're connected to UR2, and then from the Product Setup menu, select the IEC 61850 menu and the GSSE GOOSE submenu. Set the remote I/O transfer to GOOSE, the default update time to 1 second, and the GOOSE VLAN priority to the default of 4. The GOOSE VLAN ID must match the setting of the multilink switch, and so it will be set to 2. The GOOSE Transmit E-type app ID setting is once again left at the default of 0. Even though this lab does not require UR2 to transmit a GOOSE message, we'll configure UR2's name, which will be transmitted with all of its IEC 61850 GOOSE messages. From the Product Setup menu, open the Installation submenu, and in the window beside the label Relay Name, enter the name 2 in lowercase and save all settings. Now open the Inputs/Outputs menu and select the Remote Device submenu. We must define UR1 as one of the 16 relays that UR2 will accept GOOSE messages from. Enter the name 1 in lowercase as the remote device ID, 2 for the VLAN ID, and again leave the E-type app ID at the default of 0 and save the settings. The next step is to configure UR2 to extract the status of user ST bit 1 from the multicast message transmitted from UR1 and store this status in a remote input. In this lab, we'll use Remote Input 1. Open the Remote Inputs submenu. In the window beside Device, enter 1, corresponding to UR1's name that is transmitted with its multicast message. In the window beside the bit pair label, select the bit pair that contains the status of UR1's control push button, which is user ST1, and set the default state to off. The GOOSE default state selections are the same and work in the same manner as those of the GSSE peer-to-peer service. We will set events to enabled for Remote Input 1 so that the change in state of a remote input will be recorded in the event log. Save the settings and exit. As a final step, UR2 will be configured to display the status of Remote Input 1 on User Programmable LED number 2. To accomplish this, from the Settings menu, select Product Setup, User Programmable LEDs, and then select the User Programmable LEDs submenu. For LED number 2, select the operand Remote Input 1 On and save all settings. Once all settings have been saved, we're ready to test the GOOSE message configuration. When Control Push Button 1 on UR1 is pressed, LED 2 on UR2 should illuminate. If UR1 is powered down or its Ethernet cable is removed, an error will be displayed on UR2 after 3 seconds, corresponding to a time period equal to 3 times the default update time of 1 second configured within UR1. This completes the lab exercise. The D485 and P485 converters work in a similar fashion. The D485 is a Modbus to DeviceNet converter, allowing data exchange between any multilin relay or meter supporting the Modbus protocol and a DeviceNet network, while the P485 performs the same functions between any multilin relay or meter supporting the Modbus protocol and a Profibus DP network. Let's look at the operation of these converters. Data from either the DeviceNet or Profibus network is stored within the converter's internal memory buffer for transmission to the relays and meters on the Modbus LAN. The converter then acts as a Modbus master and writes this data to the Modbus slave or slaves on the Modbus LAN. The converter also reads data from the slaves and stores this information in its memory such that it can be read by the DeviceNet or Profibus masters. In either case, the buffer stores 3 different types of data: input, output, and general data. Input data is sent to either the DeviceNet or Profibus master from the Modbus LAN, while output data is sent to the Modbus LAN. General data cannot be accessed from the Profibus or DeviceNet LAN and is used for transfers between slaves on the Modbus network or as a general scratch pad for data. Either converter can handle up to 1024 bytes of general data. Note that the EnerVista P485D485 setup software program is used to configure both converters. Substation LANs can be connected to form a wide area network with the use of GE Multilin Jungle Mux multiplexers. The Jungle Mux uses time division multiplexing to combine multiple signals, analog or digital, for transmission over a single line or media. Originally designed for the unique needs of utilities, the Jungle Mux system supports a wide range of specialty traffic, including teleprotection, direct transfer trip, pilot wire, and IEEE C37.94 optical interface to protection relays, surveillance video, substation automation, Ethernet WAN IP, and telephony. High system availability is provided through redundant common equipment and compliance with Bell Core SONET standards for path-switched ring protection architecture. Jungle Mux goes beyond SONET standards, offering the industry's fastest path protection switching, less than 3 milliseconds, and incorporating special design characteristics that allow it to meet ANSI, IEEE, RFI, and SWC standards for operation in harsh utility environments. The GE Multilin SONET multiplexer is a proven platform which has been used extensively in utility applications. It connects directly to the substation Ethernet LAN. It supports a high-speed, self-healing, redundant fiber ring configuration. And it supports multiple channels, for example, Ethernet, video, and PBX, all on a single redundant self-healing fiber optic ring.